Okay, this tutorial is on a lab technique called photoelectron spectroscopy, or PES, and it's a way to deduce the electron structure of an atom. So what you do is you put an atom, like you try to put it in its gas phase, and then you basically blast it with UV photons. And the UV wavelength, if you remember from our electromagnetic spectrum, it's first there's gamma, which is the highest frequency, and then there's X-ray, which is the next highest frequency, and then after that is UV. So these are really high energy photons that you're trying to hit the electron with, or hit the atom with. And what it does is it actually jars loose an electron. Okay, so you could deduce electron configurations. You zap the atom with UV radiation, or it's actually a UV photon. So it's a UV photon. I suppose it's the same thing. So, and this energy is related to um, can be calculated actually by using a Planck's constant times the frequency. So like what we did before. Okay, so energy equal to HV. Okay, so the zapped electrons are removed from the atom, and the energy needed to do this is the ionization energy, or this may also be referred to as binding energy when you're talking about photoelectron spectroscopy. Okay, so any extra energy goes into making the electron move faster. So in other words, let's draw a picture here of let's say sodium. Okay, so we'll draw sodium. So we have 11 protons. Okay, first ring we have 2 electrons. So I'll write the configuration for sodium. So we have 1s2, 2s2, 2p6, 3s1. Okay, so on the first ring, I'm going to have 2 electrons. On the second ring, or second energy level, I'm going to have 8 electrons. So 1, 2, 3, 4, 5, 6, 7, 8. And then on the third ring, I'll have 1 electron. Okay, so here's let's draw a UV photon. Okay, so here's okay, this is a UV radiation here, and it's gonna hit this electron. Okay, so this electron, so here's what this says. Any extra energy goes into making the electron move faster. So this electron is going to have the lowest ionization energy. Why? Because, or let's use a different color. So this is going to have the lowest ionization energy out of all these different electrons here. So, and it's because it's the furthest away. So this is going to be the first electron that gets removed. Every electron after that is going to require more and more energy. So they tend to actually go according to what sub-level. So whatever sub-level they're in is the energy that's it takes for the UV photon to remove the electron. There's usually a little extra electron which makes the electron turns into kinetic energy, which makes it fly away. Okay, so this one's going to be the fastest one because it didn't take as much to remove it. Okay, and if you remember our quantum mechanical model, the little paper that we had in class, so we had a this is the 1s. Okay, and then in here, and this arrow here represents energy. So if you remember, the 2s is right here, and then the 2p is here, and this is the 2s. So the 2p is higher than the 2s. So the 2s is going to be these will be the next two electrons. Okay, so let's make that these two electrons correspond to the 2s electrons. So these would be the next ones that the photon is going to go after. Okay, so this photon will knock those free. Okay, and then the rest here, these 6 electrons right here, I'm going to circle them in blue. Actually, I only circled 5, so I'll add this one in there. Okay, those are these 6 electrons. These are going to be the next ones to get blasted by this UV photon. Okay, so these are first. So those are going to come off first. These will come off second, and then these will come off third by our photon here. Okay, and then actually I made a small mistake here. So the 3s electron is the first one. Okay, and the 2p. So this relates to how far they are away from the nucleus. So the 2p will come off second. Okay, so this is first. These are second, the blue ones. The green ones, these are third. These are third, and then these are really hard to remove. So these photons, they have enough energy to remove about 12,000 kilojoules per mole. And sometimes these 1s electrons are so hard to remove because they're so close to the nucleus that sometimes they don't even show up on a photoelectron spectroscopy graph. So they may not even show up. Okay, so to conclude, so fast-moving electrons take less UV radiation, so these must be further away from the nucleus. Okay, so this is the photoelectron spectroscopy of the first 5 elements. So let's take a look and see what's going on here. We're going to correlate this with the electron configuration of each. So here's hydrogen, and hydrogen is just 1s1. Okay, that's the configuration. So we see that this is requiring for there just being one electron. You just see one peak here. Okay, so actually the y-axis, sometimes you'll see this is you could label this as the relative number of electrons. Okay, and these on the x-axis are is energy, is actually ionization energy. Okay, and this is in kilojoules per mole here. Okay, so on helium, this is a 1s2. That's the configuration. So you'll notice that this peak is twice as high as hydrogen's. So the reason why this is further down, why does it take more energy? Well, as you know, helium has 2 protons, and hydrogen only has 1 proton. Okay, so you'll notice that this takes more energy. So this took more energy. And this peak is twice as high as this one, meaning there are 2 electrons. So look at the y-axis here. So the peak is twice as high. Because it's 2 electrons versus 1 electron for hydrogen. Okay, so here, this is an interesting one on lithium because now we've gone down a row. And as you know, when you go down a row, you get a brand new shell energy level of electrons. So let's see how that looks on the PES. So first we'll write the configuration and then try to explain what we see here based on the configuration. So 1s2 and 2s1. So this hardly took any energy, okay, and it's not that high. So this looks like it's one electron. So this corresponds to the 2s1 electron. So because it hardly took any energy because it's further away than the 1s. Okay, so that's what that peak is showing. It's showing the 2s1. Um, and this peak is twice as high, and you'll see that it took way more energy than even the helium. Why is that? Because this has 3 protons. Okay, so an extra proton holds these 2 electrons even tighter. So this peak right here corresponds to the 1s2. And again, it's twice as high as the 2s1. Okay, so here's beryllium, which is the configuration for beryllium is 1s2, 2s2. Okay, this of course is the um, beryllium. So 2s2. So this corresponds to the, I believe this peak should actually be a little bit higher. So this should be the 2s2. So where is the 1s2? Where are these electrons? It's actually so far out here that it wasn't even this photon wasn't even able to remove it, so it didn't even show up. Okay, so the 1s2 is off the charts. That's how strongly it's held. Okay, so and why is it even stronger than this one? So again, when you go left to right, it's protons. So because you have 4 protons, so it doesn't even show up. And here is boron, this last picture. So we have a 1s2, 2s2, and a 3p1. I'm sorry, a 2p1, sorry. Okay, so this must be the 2p1. Okay, because the peak looks like it's only 1 electron, and it didn't take as much energy. So this must be the furthest away from the nucleus. Okay, and this is double the size of peak, so this must be 2 electrons. So this must be the 2s2. Okay, and then again, the 1s2 is again off the charts. The 1s2. All right. So let's go on to the next slide, and I'm going to have you guys try to figure out what element this is. I'm going to put a PES up here, and then have you guys try to determine what element this is. So I'll give you a hint. Actually, we could actually conclude something here. So when you write a configuration, so let's say we have, I'll just write some random one, 1s2, 2s2, 2p6. So conclusion. Um, okay, never mind, that last slide wasn't part of it. That was a mistake on my slide. So 3p6 4s2. I just wrote whatever. I think this happens to be magnesium, but whatever. Okay, so here's so this will be the first one that shows up. So this goes first to show up, and it kind of goes in reverse order. This is the first to show up, and then this goes. So these would be the last to show on this chart. Okay, so using that knowledge, see if you can determine what element this is. And I'll give you a hint here. The 1s2 is actually shown. Okay, so it's a little bit different than the ones the examples I went to. Okay, so my slides were kind of like skipping around, so you don't need to write the other stuff. So just try to complete this question. Okay, that's the end of our tutorial.